Hi, so I am Eynat. I'm a research associate in the group of Professor Ronnie Neumann. And I wanted to start by asking, what picture comes to mind when you think of chemical industry? Probably pollution, waste, chimneys with black smoke. And what picture comes to mind when you think of photosynthesis? Green leaves, blue sky, sun shining. So let's look at one example. Let's look on methanol. Methanol is the most simple alcohol. It's a precursor to many widely used chemicals that eventually goes to the pharmaceutical, plastic, petrol, and construction industries. It produced in over 20 million tons per year, and it produced from a mixture of hydrogen and carbon monoxide that are dangerous and toxic gases. So let's look again in the industrial process. So methanol is produced from CO and hydrogen mixture, which is called syngas. Syngas is produced from methane and water, and these processes require high temperatures and high pressures and cause the emission of a lot of greenhouse gases. Nature, however, is using enzymes in order to directly oxidize methane by molecular oxygen to get methanol. And this is done in ambient conditions. So how do we bridge between these two? How do we make the chemical industry more environmentally friendly? So for that, we are using a catalyst. This is one of the main pathways to do that. Catalysts are molecules that help us to invest less energy in a chemical reaction, or in other words, to lower the activation energy, allow the use of environmentally friendly reagents, and allow different pathways of reaction. Also, nature uses catalysts, and the catalysts of nature are enzymes. And when we come to design new catalysts, one of the things that we can do is to get inspiration from how enzymes works. So in our lab, we are using as catalysts molecules that are called polyoxometalates. So looks maybe a little complicated, but it's actually just a cluster of metals, usually tungsten-6 or molybdenum-6, that are connected to each other through oxygen ligands. And those are not materials, but molecular soluble clusters. There are many different structures, and they are able to store protons and electrons on them. So how can we design the polyoxometalate to catalyze the oxidation of methane to methanol? We first look at how the enzyme works. So in nature, the enzyme that catalyzes the oxidation of methane is called methane monooxygenase. It has active site in the core of the enzyme, so it's like a confined space, and the active site contains copper metal. It also has a reducing agent that can inject electrons to the copper. So when we have the reduced copper, it can bind oxygen, cleave the oxygen-oxygen bond to get water and the active species. The active species then can take out hydrogen from methane, insert oxygen, and this is how we get methanol. So there are many groups that try to mimic or to try to find catalysts based on this enzyme. But many of them try to mimic the active site, the structure of the active site, and they are able to get the activation of oxygen, but these catalysts are usually not really effective and can't really transfer the oxygen to methane. So we are going in different approach. We are trying to mimic the main functions of the enzyme. So what we did in this project is that we took polyoxometalate in the shape of a capsule. We introduced inside copper cations, and instead of reducing agent, we are using electrochemistry. So this is how it looks like. We have our capsule with that contains 10 pores. It contains also ligands that we chose them to be with imidazole groups. Imidazole are functional groups that have high affinity towards copper. So in this way, when we introduce copper inside the capsule, the imidazole can bind and stabilize it. In this way, we were able to stabilize 10 copper cations inside of these capsules, and it's important that we will have that many of them. We also used electrochemistry to inject electrons to the copper. So how do we know that when we inject electrons, when we apply potential, the electron really goes to reduce the copper? We measure cyclic voltammetry, also looks a little complicated, but all you need to know is that this is the direction of the addition of electrons. So when we start to add electrons to our catalyst, we first get the reduction of the copper 2 to copper 1. And when we do that under oxygen, we can see that in the red trace, in the area where there is the reduction of the copper, we get increase in current. That means that we have binding and activation of oxygen. So to do the reaction itself, we dissolve our catalyst in water, we put it in an electrochemical cell with 3 platinum electrodes, and we put oxygen and 10 bars of methane, and we apply low negative potential. In this way, we could oxidize methane to get methanol and formaldehyde. And this is done using mild condition. The energy input, which is electricity, can come from renewable sources. And we are using water as solvent and oxygen as oxidant, which are environmentally friendly. We were also able to show the oxidation of different alkanes, alkenes, and aromatic molecules with this catalyst. And we did many investigations of the mechanism and of how this reaction works. I will show you only one example for an experiment that we did. So in this experiment, we compared between the rate of oxidation of different molecules, ethane, propane, and isobutane. We chose these molecules because when you go from left to right, it is easier to oxidize the molecule because the CH bond is weaker. So when we do that, we expect that the rate of reaction will be faster for the molecule that it's easier to oxidize, and we will get more product. Actually, we got the exact opposite trend. The reason for that is that isobutane, in this example, is more hydrophobic and has larger size, and because the reaction takes place inside of a capsule, eventually the substrate have to go inside a capsule, and what determines the kinetics is the size and less the CH bond strength. So that was a very interesting observation, and we have more interesting observation on the catalysis in confined space that I will not present here, but hopefully you can read it soon in the publication. So what was important for me to show you is that we can design catalysts in our lab based on inspiration of metalloenzyme, but we don't mimic the structure. We mimic the function of the enzyme. And this is not something new in the lab. We were already able to show that in a few projects. This is just a few examples that we were able to catalyze processes like the production of syngas from carbon dioxide, production of ammonia from nitrogen, and production of acetic acid from ethane. The first two is already startup companies. In this project, what we wanted to show is how we can design an inorganic enzyme, or we can design a functional enzyme by putting transition metals gas inside a polyoxometalate nanocapsule. And here we showed monooxygenase type activity, but we have already other examples in the lab for other mimic of other enzymes. And we had also a lot of interesting results regarding the catalysis in confined space. So with that, I'd like to thank the organizers for the opportunity to present my research, to the Neumann Group, and to you for your attention.